All right. Well, good morning, guys. Today we are going to cover the second lesson in grade 11 University Chemistry. And we'll try and get through this one fairly quickly. So I quickly want to just review stuff we talked about yesterday, which is we know that there are three subatomic particles. We know that the atom is made up of protons, neutrons, and electrons. And if you remember, we said that the protons and the neutrons basically weigh the same, right? So a proton weighs 1.00728, a neutron weighs 1.0087, and an electron weighs 0.00055 atomic mass units. And I want to stress that this atomic mass unit is just kind of an arbitrary weight. It's basically a unit we invented that is exactly the mass of one proton. And another time I'll tell you exactly how it's calculated, but it's basically the mass of a single proton. And so taken roughly, protons have a mass of 1, neutrons have a mass of 1, and electrons, if we're rounding, basically have a mass of 0. And yesterday when we talked about that table you had and calculating how many protons and neutrons and electrons there were, excuse me, those were kind of the assumptions we made. But I just want to say, based on these numbers, what should be the mass of a hydrogen atom with 1 proton and 1 electron? So what should be the mass of a hydrogen atom with 1 proton and 1 electron? Well, we can show it here. The mass of hydrogen should just be the mass of 1 proton plus the mass of 1 electron. And with that in mind, it should be 1.00728 plus 0.00055. And if you do that math, you should get 1.00783. Doesn't change much. That's what we should get as the mass of hydrogen. Now, I've also asked you to calculate the mass of a sodium atom, and this one with 11 protons, 11 electrons, and 12 neutrons. And just if you want to take a minute, pause this video, see if you can work it out yourself. See if you can figure out what the mass should be. All right, I'll assume you've come back, and we'll say, well, really, it should just be 11 times the mass of a proton, plus 11 times the mass of an electron, plus 12 times the mass of a neutron. When we do that, we should get 11 times 1.00728, plus 11 times 0.00055, and plus 12 times 1.0087. And you can plug that into your calculator, and hopefully you got the number 23.191 atomic mass units. By the way, I've shown it in 2 steps here. There's no real good reason to do that. You can punch that whole thing into your calculator in 1 step. So let's think about that for a minute. And if we go to the next slide, what I've asked you to do is ask, how do these numbers compare to the values given on a periodic table? And we can fill them in, all right? Hydrogen, that number we calculated, 1.00783, can go right in here. And sodium, that number we calculated, 23.191, can go here. I've put a third example in, calcium, which we didn't do the math, but if we had, we'd have calculated that calcium should have a mass of 40.3306. And so what I want to ask then is, if we look on the periodic table, what do we find? And if you look on the periodic table and look up the mass of hydrogen, you're going to get a slightly different number. You'll get 1.0079, which this should round to 7/8. So they're not exactly the same, though they're really close. Then sodium, where here we get 23.191, the periodic table shows 22.989. It's smaller. And for calcium, where we get 40.3306, the periodic table gives us 40.078. None of the numbers match up. And so the question is, why are they different? And there's two reasons. There's two reasons that aren't the same. The first is a really weird one, but it's actually that the mass of protons, neutrons, and electrons can actually change a little bit. Now, we don't have to worry about that, but it is true. When they form a bond, they actually change mass, which is kind of weird and not something you need to worry about. But the second one we really need to worry about, and that's what today's lesson is really all about, which is that when we look on the periodic table, the mass it gives us is an average atom of that element. Because we're going to discuss today, all of those elements are not necessarily the same. They're not necessarily identical. And that brings us to the topic of today's lesson, isotopes. All right, not all atoms of a particular element are identical. In fact, while the number of protons and electrons must remain the same, different atoms of the same element may have a different number of neutrons. Remember we said that 11 protons, by definition, is sodium. And that's true by definition. But the number of neutrons doesn't change the chemical identity. So you can have sodium with extra neutrons or neutrons taken away, and it still stays sodium as long as it has 11 protons. All right, we call the different versions of these same atoms the different isotopes of one another. And remember, neutrons have mass. They weigh approximately 1 atomic mass unit. So every version of the atom, every isotope of the atom that has a different number of neutrons is going to have a different atomic mass. All right, so this is all a little obscure, but let's take a look at hydrogen. There are 3 isotopes of hydrogen, and this should be on the note in front of you. The first one we call protium. This is just standard old hydrogen with 1 proton and no neutrons. The second is called deuterium, and it's 1 proton and 1 neutron. And the third one is called tritium, and that's 1 proton with 2 neutrons. And I was going to draw this here, but then I thought I'd get a picture. So here we are. Protium is 1 proton in the center, 1 electron in the orbital, and that's it. It has a mass of approximately 1, right? Because it's just got the proton. The electron weighs essentially nothing, remember. Whereas deuterium has a proton and a neutron in the nucleus. And so it has a mass of 2. It's still hydrogen, because the definition of hydrogen is any atom that has 1 proton in the nucleus. But it's hydrogen that weighs twice as much. And in fact, here we have still 1 proton. So this is still hydrogen, but this has 2 neutrons. And so we call this tritium, and it has a mass of 3 atomic mass units. So we can have hydrogen that weighs 1 atomic mass unit, or 2, or 3. And the difference between them is the number of neutrons, 0, or 1, or 2 neutrons. And these are the 3 different isotopes of hydrogen. All right. How do we write this? Well, we notate isotopes this way. We write the letter, the formula, all right, chemical symbol, and then down here we put the atomic number. All right, that tells us how many protons. And up here, we put the mass number. And that tells us how many protons plus how many neutrons there are. You'll note that this notation is not like we normally write it on the periodic table. It's a little wonky, and I'm sorry for that. I didn't invent it, but that's how it is. Now, this leads us to the last idea we're going to talk about today, which is that some of the isotopes of an atom are more abundant in nature than others. And that word abundant just means how often we find it. How much of it is out there? So for example, in my chemistry class, there's roughly equal abundance of males and females. I know in my second period class, there's 12 females and 11 males. And that is their abundance. The abundance of females is 12 out of 20 out of a total of 23, and the abundance of males is 11 out of a total of 23. So abundance just tells you how many of them are out there, or how many we find. I don't even know what I did there, but that's okay. Right? The average atomic mass of an atom is calculated using a formula. And it looks way worse than it is. But to find the average mass, we have to take the mass of the first isotope and multiply it by how abundant that isotope is. Then we have to take the mass of the second isotope and multiply it by how abundant it is. And we keep doing this for however many isotopes there are. So if there's 3 isotopes, we just have to do that 3 times. If there's 7 different isotopes, we'd have to do it 7 times. So this is all kind of theoretical, and it can be a bit confusing. The last thing we're going to do together here is one example, and then I'll give you some homework to practice this, and we'll take that up tomorrow. So we want to calculate the average atomic mass of carbon given this, given a little chart. All right, and what we say is that the average atomic mass of carbon, we said, is going to be the mass of the first one, and I'm going to call it carbon 12, right? So carbon 12, right here, we're going to multiply its mass by its abundance. And then we're going to add that to the same calculation for the second isotope. So what I want to remind you of here is that what this means is that there's 2 types of carbon out there. There's carbon that has a mass of 12 and carbon that has a mass of 13. So this would be 6 protons and 6 neutrons. That's the first isotope, 6 protons, 6 neutrons. The second one would still have 6 protons, because that's the definition of carbon, but then it would have 7 neutrons. And again, you don't have to know that necessarily, but just explaining where the 2 different isotopes come from. So we get the average mass by multiplying the mass of the first isotope by how abundant it is, plus the mass of the second, so the mass of carbon 13, times its abundance. The abundance of C13. And with that in mind, we can say the average mass just works out like this. Looking at this table, I know that the carbon 12 has a mass of 12.0000. 12.0000. And then its abundance is 98.90%. And remember that we're always going to do math like we always do with percentages by expressing it as a decimal. So hopefully you remember how to express a percentage as a decimal, but we just always move the decimal place twice to the left. So we would say this is 0.9890, and that's the abundance that goes here. 98.9% is written as 0.9890. And then we're going to add that to the mass of the carbon-13, and that is 13.003355. And we're going to multiply that by its abundance. And again, remember, we move the decimal twice over. So here once and twice. And to move it there, I'm going to have to put a placeholder 0 here. And this becomes 0.0110, just like that. And when you put all that into your calculator, so go ahead and do that. I'll do it on mine here. What you should get is 12.011. Nope, can't read. Yeah, okay. I'm sorry, I can read. That's exactly right. 12.011 atomic mass units. And that's the mass. I'm going to change colors here. I can figure out how. That's the mass of an average carbon atom. And what I want you to notice is that there's no such thing as a carbon atom that weighs that. Some carbon atoms weigh 12.000. Some weigh 13.003355. None of them weigh 12.011. But that's still the average. Just like if we took Jack Cook and I, Jack Cook is, let's say, oh, one sec. Jack Cook is, let's say, 11 feet tall. I think that's accurate. And I'm, let's say, oh, I don't know, 5 feet tall. If you take our average height, you'll actually get 8 feet. Now note that neither one of us is 8 feet tall. He's 11 feet, I'm 5 feet. But when you take the average, you get this number in the middle. And that's how this works too. It'll tell you the middle value. And that doesn't mean that any one person has that height. And in fact, nobody does. Likewise, it doesn't mean that any one carbon atom weighs 12.011. It just means that this particular one did. So you'll see once you get doing this, that's really not a difficult calculation to do. And I'm going to help you along the way. Sorry, by giving you a bit of homework to do. So you'll find that attached on the OneNote, and get to it. And if you have any questions, again, don't hesitate, don't be shy. Come get some help from me. But that's the end of the main lesson here. So thanks for sharing along.